Thank you everyone for joining today's webinar from Enterprise Neurosystem Group. Our speaker today is David Tennenhouse. He needs no introduction, especially in the networking circles. He has been through the academic MIT, where his work on active networking was well known. He has been in various government agencies, sponsoring multiple projects and programs. He has been with venture capitalists and also at UC Berkeley, and now as an independent researcher. David has introduced a great new notion of surprise networking, and we are thrilled that he is here today to explain that notion to us in Enterprise Neurosystem Group in more detail. Over to you, David, for the conversation, for the presentation.
Well, thank you, Dinesh. And just before I get started, or as I get started, I just have to make a couple of disclaimers. And they're basically that until about a little over about a year and a half ago, I was at VMware. And when I left VMware, they were kind enough to let me take some of my PowerPoint with me. So some of those slides have VMware logos, but I'm speaking here for myself and not for VMware. Similarly, I'm currently working with the National Science Foundation, and again today I'm speaking as an independent researcher and not on behalf of the NSF. So with that in mind, I want to especially thank Dinesh not just for hosting me today, but actually for kind of prompting me to go down this path. A while back, Dinesh asked me to join a workshop in which speakers were asked to talk about what we thought networking would look like 70 years into the future. And my first reaction was, whoa, that's a long time. I'm good at sort of the 10 to 20 year time frame. I'm not sure how to think about that. But then as I thought about it, I realized that these network infrastructures that we put into place are very long-lived. So, if you look at telephony, for example, telegraphy had a very long lifetime. And it's interesting to see, so, what were some of the key elements? And for today's talk, since I know this isn't primarily a networking group, I'm not going to go into all the network details. So just the short form is that although we think of telegraphy as being about Morse code, that's how it initially was implemented. Even Morse code, if you think about it, was taking information and reducing it to symbols, dots and dashes that then represented alphanumeric characters. So there was already some information theory getting used there. Also, very quickly, they evolved to actually, having the messages transferred onto paper tape, and then the paper tape could be played through over the expensive wires between cities at faster speeds than the humans could type at. So we sort of saw the use, essentially the paper tape was a form of storage in the network, and these were store and forward networks with, you can think of it as the forwarding, the computation being done by humans. So if we then kind of roll forward, we see that circuit switch telephony, which, eventually took over from telegraphy, but the two overlapped for many decades. It, actually used some of the same mechanisms. It started out with the storage switches, but if you think in terms of underlying mechanisms, we introduced stored program computers that initially just controlled think of it as they decided what the routing of the call would be, and they controlled the mechanical switches. So we started using computation in the network to control the switching. As we digitized the network, we actually essentially added storage. Today it seems kind of laughable, but we kind of put a couple of bytes of storage for every subscriber into the network because we were sampling the telephone calls and needed a place to store those samples as we then routed them through fully electronic switches, which eventually evolved in the 70s and 80s. So there, we were putting storage into the network. And in addition to the computation and storage, the key to that was just the whole basis on which we were sampling the analog calls converting them to digital was, deeply grounded in information theory. So again, information theory plays an important role. In the internet, we just kind of went wild with, lots of computation. You can think of it as telephony did a computation per call to figure out which way to route the call. And, in the packet switching world, we were doing a computation on every packet. We went wild on storage. You started having packet buffers. So now you were storing not just sort of a byte per line, but many packets of information per switchboard. And of course, we used a lot of compression over time, et cetera, on a more end-to-end basis, and sometimes even hop by hop. So information theory was playing its role. But at the same time as we were really rolling out the internet, cellular access really changed the whole access network. And it was very, very deeply rooted in the use of information theory, how to get kind of more bits per hertz out of the wireless spectrum. And in fact, a parallel activity went on with the wired network, both with systems like DSL and, more important, with hybrid fiber coax. So huge run of information theory. So the higher message here is, over a multi-hundred-year kind of basis, the tools of the networking trade have been, more and more computation in the network, more and more storage in the network, and really more and more use of information theory. And in fact, a lot of the use of the computation and storage today is the mechanisms to put the information theory to work. So, there's been another change going on, since we rolled out the internet and since the change in the access networks, which is the network has actually evolved. Those earlier infrastructures, including the original internet, were really intended for end-to-end communication between sort of, subscribers at each end, whether it's, telegraph messages or telephony calls, et cetera. But today, our communication is really edge to cloud. Now, I'm not necessarily saying where in the cloud here, but what I'm saying is that even when we're doing things between two people, like, for example, or multiple people, even today's video conference here is being mediated by services in the cloud. So really, it's kind of an edged cloud for many people, with the cloud service pulling us all together. And as this evolved, the big cloud players started realizing that within their major cloud data centers, they could build the networks internally any way they wanted. So we started getting very customized, say, non-TCP/IP or not pure TCP/IP networks inside their data centers. And then they started realizing that they could interconnect their data centers with their own private networks, and they could start pushing their private networks kind of closer and closer to the edge users. So although we think of the internet today as a globally interconnected network, sort of almost it's better represented by thinking that we've got these big hyperscalers shown here on the right running their own networks. They may run TCP/IP and protocols internally. They may run customized protocols or hybrids. And on the left here we have the access providers, and they could do whatever they want in their networks. And really, the internet protocol is just being used in a very small, or it's only necessary in a very small part of the network. So we really have got a sea change there going on, kind of under the covers, and all part of this change from end to end to edge to cloud. And I'd say that transformation from edge to cloud is, we're just starting on it. We're just only part way through. So, some of this talk is about what's next. That is, kind of what Dinesh asked me to speak about at that workshop back when. And the spoiler alert here is that I think that some of the key opportunities are going to be near the edge, at that point that I indicated, where the hyperscalers that run their own networks and deliver traffic almost to the end users meet the access providers that provide the services to the end users. So if we were thinking about how might we redesign things for that edge to cloud world, where we're really the action is near the edge. There's sort of a set of design requirements that I think of as evergreen. Any future infrastructure is going to have to look at these. And these are good requirements, but I'm not actually going to try and discuss them today because I think that anytime you do, you probably will end up coming back to something close to what you have today, as opposed to breaking out into something of the future. So instead, I wanted to just, talk through briefly what are the other questions besides these that we should ask ourselves. One that I always think is important is to look and say, what will be in surplus in the future? Is there something that's scarce today that because of technological change is actually going to be much more affordable and more in surplus in the future? And I think two of those things, both near the edge, are going to be that our edge capacity is growing greatly. 5G kind of, promised gigabit per second to the individual user. It's not going to really achieve that, but let's say 6G does. So in other words, again, in our long-term time horizon, we're getting very close to the point where you'll have more capacity at the edge than you actually really need at this at this point in time. So we're going to kind of transition from a shortage of edge capacity where the edge channel is always slower than we would like to a point where we have some headroom. And then what will happen is applications will use that up, but the technology will keep getting better. So this is kind of a one-time transition to a point where we can really start thinking about doing fairly extravagant things at the edge. The other thing is that I think we're going to have a surplus of high-resolution sensors, and I won't get into the rationale for that, but just think of this as we're going to have much, much greater ability to collect information at the very edge of the network from the users and their surroundings. So we get this opportunity now to finally realize cost-effective, high-fidelity instrumentation of the physical world, something that we've dreamt of for the past few decades, but now we're going to have it. I think the implications of that for applications is that we can now start thinking of proactive applications much more aggressively than we have in the past. And by proactive applications, I mean applications that anticipate our needs and sometimes act on our behalf. And we're already sort of seeing that with what you might think of as non-real-time applications. And I think now we can bring those into the real-time and closer to real-time world and really bridge the physical and virtual world. So when I think of these proactive applications, they're edge-to-cloud systems that really bridge the physical and virtual world and take actions ahead of our needs. So they're sort of working on the answers before we ask the questions. And there's a number of examples. I'm not going to go through these one by one, but I just want to get across that proactive edge to cloud can really be a different paradigm than end-to-end or even today's edge-to-cloud environment. So, having looked at what will be in surplus and what do we think the applications will look like, so how do we use the tools of the networking trade to enable proactive edge-to-cloud? I think, we'll have a lot more computation in the network. I think people see lots of ways to do that and that will happen. I think, less appreciated is there'll be a lot more storage in the network. We've actually had a few decades of research on how to think much more about a network where content just sort of moves freely through, and effectively through the network. So by freely, I didn't mean that as a people paying for content or not, but simply content easily moves through the network, and the network's much more tuned to moving content. So I think, I'm not, again, going to go into detail on this, but I think we may see that we'll have not only much more storage in the network, but some of these information-centric or name data networking concepts will really come to fruition, particularly near the edge of the network. However, I think the main focus of this talk is okay, but what about information theory? What role will that play? And my answer to that is surprise. And what I mean here is kind of an observation, and this is, I'm going to say right up front, a hand wave, that the information content of an event or of a message is really just depending on the degree to which the content of the message is surprising, right? So, if I send you a book one day and then I send you that same book the next day, there was no surprise in that second transmission. So even though it might have used up, a lot of bandwidth to get there, there was actually no information value being transmitted. That was old news, right? So, conversely, if I send you, if I toss a coin, you have no idea if, I found that to be heads or tails. And so if I send you the result of that coin test, that has a very high information value because it's surprise, you didn't know it. So, with that observation in mind, I guess what I want to do is think about, how we've been thinking about content in this edge to cloud world to date and how we might think about it differently in the future. That's really the core of this talk. So the simplistic interpretation of surprise is that kind of everything we do in edge to cloud today has no value, because mostly what we're doing today is taking, old information that's stored in the core of the cloud and delivering it to the edge on demand. Now, that's, I think, obviously too simplistic. So I think a more realistic interpretation is that going forward, high value is going to be created by the fusion of new information and the new information comes from the edge. It comes from, the physical world, the users and devices and sensors and all of that's in the physical world. It's at the edge of the cloud. And fusing that new information with the priors, with all the previously known information that's at the, coming from the core of the cloud, that's where we're really going to create value. And the more we can do that in real time, the better. So, I think the message from surprise is that we should be really thoughtful about how and where old content's combined with new, and that's kind of going to be the key sources of value going forward. And it suggests, for example, and this goes back to the proactive notion, that we could be very aggressive about opportunistically computing or speculatively computing on that old information to come up with answers, even, as I said, before people ask the questions, and stage the results of that pre-computing within the network. And I'm going to say not only, within the network, but close to the edge of the network, close to where we're going to want to fuse it with the new information. So here's a very simplistic, again, hand wave diagram of what that might look like. You've got the old information in the core of the cloud, new information coming from the edge, and by the edge again here I mean kind of the users and their devices that are kind of right at the very edge of the network, and from the core towards the user, you can imagine that we want to do this opportunistic computing and perhaps also geo-shard the information so we can get it to the right subsets of the information to the right edges and cache it somewhere inside the network. Coming from the edge, you're going to have information coming from many users. Ultimately, you'd like some of that information to get to the core of the cloud, but you can do a lot of interesting aggregation, filtering, and compression within the network. And then the most important part is somewhere, again in the network, and I'd argue near the edge, you want to fuse those two and get those results back to the edge on a timely basis. So if we think about, where we should leverage surprise, it's a trade space, right? Right at the very edge where on the user's devices, and we can imagine in an AR world, VR world, it's perhaps, right in the user's glasses. We have very low latency. However, we have very limited power. And we're not really getting good sharing of the computational horsepower of the storage because it's really dedicated to the one user. Deep in the cloud, we have the advantage of high sharing and abundant power, but unfortunately we have high latency, getting that information from deep in the cloud to the edge. So my argument here is that there's a Goldilocks zone in what I'm going to call near the edge, and that's where we should really be trying to put these new capabilities. And near the edge is a fuzzy definition. I'm going to try to refine that a little further by putting a stake in the ground and saying we should try to do this approximately within 1 millisecond of the sensors, actuators, and people. Now, by 1 millisecond, I mean sort of, draw us, the outer circle here is about 1 millisecond speed of light distance from the center of these concentric circles. So what you should take away here is 1 millisecond is a really big circle, right? Now, you might wonder, why am I interested in, kind of 1 millisecond? And I've just chosen that somewhat arbitrarily, partly because, these are very big circles, right? We can be quite generous with them. But the reason is that will give us low latency, but, in a realistic and best effort paradigm. And really what I'm shooting for is, could we give the applications 10 millisecond round trip time latency? So if you think about it, okay, so if I've got 1 millisecond, one direction, that's 2 milliseconds round trip time, but there's going to be, some computation to be done near the edge. There's going to be computation done, back at the edge itself. There's, various, buffering, all sorts of things. So it seems like if we, within these 1 millisecond circles, it should be practical to achieve 10 millisecond application latency. And, part of what I'm arguing here is that would actually be good enough for the vast bulk of applications that we really imagine doing. And, I can, take some questions later if people want, but essentially, 10 milliseconds is fast enough for any of our human response time. It's actually fast enough for our human vision system. You could make arguments that there may be devices, robots, etc., factory automation, vehicles, things that would like to have even faster response times. However, I'd argue that in those cases, you are, for various reasons, and most importantly, reliability, are likely to actually put that faster, feedback loop in the device itself, in the edge device. And so for things where we're trying to fuse the old and the new, I think we're going to find in most of the practical applications, 10 milliseconds is going to be plenty good enough. And it's going to, I think, enable some really interesting things. One is we can do very smart upstream delivery of the new content. So we can, sort of have these near the edge capabilities that are going to do interesting filtering, different types, essentially of compression of these feeds, aggregation of nearby feeds to combine things, lots of opportunities there. And as I said, there's going to be opportunities to stage the old information coming from the deep in the cloud near the edge within, that 10 millisecond round, kind of application response time, and synthesize the new and the old. So you essentially think of it as that for the purposes of any given application, all of the priors have been pre-digested, staged nearby, so they're ready to be fused with the new data, and the results can be automatically pushed to the interested edge parties. So I really feel like this near the edge is kind of a magic place. It's close enough for latency purposes and deep enough for sharing purposes. And I believe that, a number of folks in this particular group, and that's, part of when Dinesh asked me to speak to this group, are already kind of recognized this and dealing with this. So, and trying to create new functionality in this near the edge and 10 millisecond kind of response time regime. So I don't believe I'm really giving you something new so much as perhaps a framework to think about it, and maybe a rallying cry with surprise to rally around. Now, there are other reasons also to want to be near the edge, like sovereignty and privacy, and that's one of the reasons why there's a lot of interest in federated learning. So federated learning can both be a good thing to do from a low latency perspective of being able to update models that, where the models need to be updated really quickly. You could update them quickly and locally, while over the longer term evolving your global model. However, I think federated machine learning also has some privacy benefits of keeping the information essentially closer to the edge, and not pooling all the information in one global place. And finally, I think this near the edge, as I indicated before, is where the cloud providers are going to meet the local access providers. So there's kind of, a whole bunch of interesting questions about, regulatory, competitive market issues, et cetera, to be resolved. So I think there'll be some, it's an interesting place to create this, this new functionality. So in the remainder of the talk, what I really want to do is just talk a bit about the programming model, because I think that's the part that may be most appropriate to this group, in a place where I'm actually hoping this group will drive things forward. So, this was the simple diagram that I provided before of, kind of caricature of the type of processing that's required. One of the things it suggests is we're going to have to get really good at hosting application functionality near the edge. And that means, having the tools to deploy and operate code with security and privacy and multi-tenancy. The good news here is that actually we're starting to see examples of this come out already with things like AWS wavelengths, Cloudflare workers, and we're even starting to see perhaps WebAssembly emerge as it might become, the kind of the programming language for much of this near the edge functionality. So that's good. Our kind of ability to put pieces of code near the edge is starting to show up. We don't yet really have the edge storage, I think, that we would, like to see. So that's, I think, an opportunity. And then most importantly is what I think of as the higher level mechanisms to uncover and act on semantic surprise. We don't necessarily have to figure out how to do this in the most general way. If we could find, a few key applications that are heavily reusable, or a few key, heavily reusable pieces of functionality, that could get kind of the ball rolling. So we'd like to, basically figure out ways to make it less painful to create surprise-inspired applications. So I'm just going to here roll through some suggestions of things that might help us fuse new information from edge devices with old information coming from the cloud. So, one aspect is that I think, BitTorrent had a very interesting innovation that I call the recipe model that I think did not quite get enough attention, which is simply that, in the BitTorrent world, you take your data, you chop it into pieces, you sort of dump it into the network, and then you separately provide people with the recipe, the torrent file that says, if you want this information, if you want to recreate this, you just have to get these blocks and assemble them in this order. So in other words, you've separated out the business of depositing the thing into the network from the business of being able to get a copy back out. And the person getting the copy out doesn't really care where the pieces of the copy came from. And I think that separation could be very powerful, and may be able to use it in additional ways. Another thing that we might be able to reuse, mechanism that we may be able to reuse, is simply a lot of these applications are going to be, geographic, where we're going to, I alluded to this before, we're going to be sort of geo-sharding the information in some way, or want to, the user near the edge wants to focus on the information that is in their environment, near them, information coming from other users close by, etc. So this could be information that's from other users near the edge. It could be information that is coming from deep in the cloud, but relevant to where they are. So I think that, the use of GIS-based sort of labeling could be very powerful here. I think it would be great if we could build a new capability. We have CDNs for, including BitTorrent, for moving information essentially from the core to the edge. It would be wonderful to have a reusable, what I think of as inverse CDN, that would help the flow of information coming from the edge and do filtering, aggregation, forwarding. I indicated some of that in my little block diagram earlier. Starting to see the beginnings of something like that. There's something called a data aggregation networks that the folks at Austin have been talking about. But that could be an example of, what I'm trying to get at here is what could be reusable mechanisms that could then be used to build a bunch of applications. I think something would be very powerful. I've always felt like declarative methods, like the database people are able to separate. You put your query in a language like SQL, and you don't have to think about how is the data stored. The database takes care of that. So you just express, in a language like SQL, you declare, here's the shape of the answer I want, and the system goes and gets it. So I think extending, that sort of thing to be much more dynamic would be great. There's some work by, Netravalli at Princeton, and he's actually in a joint project with others as well at other places on kind of a video analytics query language. So you could imagine that you have not just one-time queries, but you have standing queries. So you issue your query once, and on an ongoing basis, it's updating things. Now, standing queries have actually been a dream in the database world. It's often referred to as materialized views. And something that I think is quite exciting now is two groups. There's have been working on differential data log. I've referred particularly to some work by my colleagues at VMware on differential data log and something they call DBSP here. But the thing that they've been able to do is really facilitate this notion of using incremental computation. So in other words, what you want to get away from is that every time you ask the query, you have to go back and get all the data and relook at the query. You'd like to be able to, as new data is coming in, update the answers to the query. And again, that's the dream of materialized views. And I think some of this recent work that they've done and some other folks is really sort of making this possible now. And if we could bring that, not just make it possible at the core, but bring it to this near the edge, I think that could be a really great reusable capability. And so, if I think specifically, some of those prior things were reusable for near the edge computation and storage, but I think specifically about uncovering surprise. I think these declarative methods, especially the materialized views I just spoke about, would be very powerful there. I think something, and again, it's something that I believe that people in this group are working on quite aggressively and working on it near the edge, is that machine learning's separation of training and inference is really kind of a very powerful concept, right? Because in effect, and it's very, kind of got a very information theory-like approach. So if you think about it, the training compresses all the prior data into a multidimensional space, which is model parameters. So we basically, that's like a compression step. We take all the training data, we compress it, we get the model, and inference is actually processing the surprisal, the new information, to determine, how it aligns with all that old information, which part of the space the new information aligns with. So, what I'd argue here is that training and inference separation of, compress all of the prior, and then have a mechanism to align very efficiently the new with the old. That first off, we could just use that in an ML context to uncover surprise. But what we should also do is try to find ways to essentially generalize this design pattern. So for example, we may be able to there may be other kinds of compression than we think of with machine learning compression for compressing the old, and other ways of kind of doing the equivalent to the inference step. And, sort of playing into this is a concept that, Butler Lamson pointed out to me, which is that, when we build many systems that are real-time or near real-time, what you actually want to do is divide it up into a sort of set of local predictions that are going to be very fast. So have a way, that you locally or very quickly can get a prediction that's usually good enough. And then have higher fidelity predictions that are based on access to more information that maybe take a little bit longer. And then build a system that's very good at combining the two of these types of, kind of predictions of where the system is going in the future. So think of those as the answers that you're going to want to have. So in many ways, again, people are doing this with machine learning systems. They're sort of combining small models that they might operate at the edge to get an immediate answer with longer term, more informed models. And by the way, these could be machine learning based, but you could also do this with physics based models that are basically looking at laws of motion, et cetera. And that's a very popular thing to do with augmented reality and virtual reality. There's, I think, an interesting project here going on by Yates and others. Again, this is a combined project, so it's Rutgers people and people elsewhere as well, where they're using something that's called the age of information analysis to essentially achieve a best effort latency. And you can think of this as they run that, the faster model and the slower, better model. Basically, when they can, they try to update the user's worldview with the longer term better prediction. But they are always looking, they realize that sometimes by the time the answers come back from the core of the cloud, they're no longer valid. So this is where the age of information aspect comes in, knowing kind of when to discard things and replace them with things that are perhaps more up to date, but lower resolution. So to sum all of that up, I think, if I look over this long time period, where we've benefited in networking, and I'd argue also in geo-distributed systems of the sort that I believe this group is looking at, is, we put more computation into the network, more storage, and now, what I think looking backwards is where we've really benefited, the big lever's been information theory, and I'd like to encourage people in this group to apply, particularly the surprise aspect of information theory that tells us that we should be really thinking about how to fuse the new and the old to the design of new systems going forward. So with that in mind, the key summary here is that I think there's a chance to reimagine computation and communication through the lens of surprise, create new generations of applications that are hosted near the edge. And along the way, move kind of beyond the mindset of 3G, 4G, 5G, and really think about how do we deliver whole new types of edge to cloud services. Thank you.
Well, thank you, David. That's a very interesting talk, full of surprises. So thanks. I have a few questions myself, but before that, I wanted to check any of the members, listeners. Do you guys have a question? And I would request when you ask a question, come off, unmute, turn your video on. And if you don't mind, just say, just state your name and also your organization, just so that we can have it for the record. So any questions, please? Okay, since no, okay. Hi, Leo, please go ahead.
That was extremely interesting. Thank you for that. This is one of the few I'm going to have to review the video of this to go through it again, but I believe I get it. It's absolutely fascinating. I'm very familiar with sharding, use it all the time, but in various applications. Specifically, what is geo-sharding in your earlier model?
Sharding, think of it as just based on geographic information. Right, so where you're able, to sort of shard the information out, so you're able to push it out to the different parts of the edge, so that, each edge gets the subset, the shards of the information that are most appropriate to it.
Based on
geographic location.
Specifically.
Yeah.
Doesn't that then isolate information in corners of the geography, if you will, and it limits surprise and tends to cluster in specific areas?
I think it's a kind of a very interesting trade-off, right? And this also, has to do with sort of say the long-term versus the shorter-term question, the old information versus the new. So let me just see if I can get back to diagram here without killing too much time. So, I guess what I'd say is you'd end up with some of the information again cached out near the edge. So, you had geosharding in perhaps your system in the core that made it efficient for you to be able to push it out to those caches. What that says is that edge,
I see.
interestingly, that edge has now been informed. What you shard out to that edge or what you push out to that cache, right, may not only be information that it certainly wouldn't only be information that came to the edge. So for example, think of it as perhaps part of a machine learning model that has benefited from widespread collection, right, from many other places. And you've pushed out the parts that you think are most relevant to this area, right?
Got it.
You may get that wrong. And then notice in the upstream direction that on the one hand, you kind of want to locally benefit from the new information right away, but you push subsets of that new information to the core of the cloud so it can be pooled together. Right?
I see it. I'm sorry.
So
This is so much fun. Got it.
Yeah.
I got it. Thank you.
Yeah, so on to the left you have kind of a shorter time constant process, and to the right hopefully you have a longer term gestation. Now the last comment I'll make here is that there of course will be cases where you actually do want to isolate information and kind of keep it compartmentalized, right? And not necessarily have everybody's private information flow to the core. And again, federated machine learning, I think, is quite interesting here because can you cause the essential parts of that information to move to the core so we get the benefit of a broader, kind of gestalt to the whole community without the sort of detailed high resolution aspects necessarily moving to the core.
Excellent. Thank you. That's, I think I have it. I have a better grasp, but it's still going to take some contemplation, but this is absolutely fascinating. Thank you for that.
Keep in mind, I freely admit this is a hand wave. So, some of the depth and the detail, isn't there. And I'm counting on folks like yourself actually to go out and, not just, both interpret it and put meat on the bones.
Great. Well, thank you.
Thank you. Vikas, please go ahead.
The speaker may be on mute. I'm not hearing him.
Yeah, Vikas, you're on mute. Can you unmute yourself? And
sorry about that. Can you hear me now?
Yes, that's good.
Okay. So what I was saying that, first of all, thank you so much. A very interesting topic. And this is Vikas from Reliance Jio India. My question is related to, I recently heard one AI related camera which does not even have the lenses, so it does not pass the information in terms of the text and things like that. So it's like minimizing the information that you transfer from one point to another point, instead of transferring like whole image. It will have some AI related text that, okay, today is the sunny weather, so this is the location. So you like compress the information too much. So from that concept to this concept, so where do you see the future will look like? Is there less information, or is the same information is stored at the different places and combined in a different way?
Well, I guess, there's a few different things to unpack there. First, I'd say I think those sorts of cameras and devices have been long overdue, and I have also seen some of them now coming out. So think of it as, there is a camera chip there, but what exits the edge device and goes into the network is only the subset, the digested relevant subset of what that camera lens saw. And I think that is a sort of filtering that's probably overdue. So in that case, you would have less information coming from the edge, initially, and you just have sort of the signals, relevant signals moving in. I think we'll see some of that. However, I think what we'll on the other hand, find is that for many, many cases where it's not highly privacy sensitive and where you remember I said, I think we'll have a surplus of bandwidth. People will find that they do want to, try to collect the more detailed, higher resolution information because they may find other applications for it in the future, right? So this is often, something we found is, later we deploy a system and then we later realize, well, there's a number of other things I could do with it. So I think we'll get both, and I really welcome these more, narrow, think of it as narrow aperture systems, particularly for, privacy sensitive things. I think we're also going to get a third thing that is quite interesting, and some of the folks I referenced here earlier are looking at it, which is imagine a camera system that knows that it's not a human being watching it, it's a machine learning model watching it.
Cool.
And therefore, the information can both be, kind of compressed. You can think of it as you may add more resolution to parts that are informative to the machine learning model, and essentially compress or pull away and discard the aspects that would have been more human oriented. So I think, and by the way, you can also imagine a feedback loop there where the model actually informs the device. Here's what I could benefit from. I think that's really intriguing, particularly as we go to sort of more multispectral and hyperspectral type systems.
Okay. Thank you so much.
Okay, thanks, David. So, David, I have a question, if I may ask. This is Dinesh Verma from IBM. I mean, like in your talk, you basically associated surprise as something new that is coming, new information, new intent. Now, that is in some sense very much decoupled from the geographic location, whether it's at the edge or at the cloud. Much like in the machine learning, you can do both training and inference at the central location, or you can distribute them to the local or edge depending on the network bandwidth characteristics, regulatory constraint that you mentioned. So I'm just wondering, for this novelty of information, the old information, does it have to be coupled to the edge and the cloud construct? Can't the determination of the new information just be done by a cloud service, especially at the application levels? Or if the network is fast, is your concept independent of the edge cloud split, or is surprise something which is inherently tied to the geographic separation of edge and cloud?
Well, so that it's a great question with a few different pieces. So let me first say, I certainly don't think it's that everything, for example, would be geo-sharded, right? I was simply saying that it may turn out that for many I'm looking for like, where could we find building blocks for building applications? So if it turns out that the application of interest has a geographic component, strong geographic component, and I think many of them will, wouldn't it be great if we had some geographic building blocks, right? So think of it, that way. In terms of the broader question you're asking, first off, I think that absolutely the main observation, which is that we should be thinking much more about how to fuse the old and the new. That could definitely be done in the core of the cloud. It can be done near the edge. It could be done in the middle of the network, right? And in some ways, the easiest place to do it is probably in the core of the cloud, right? Because we get high reuse of resources. We don't have power shortage. There's resilience. So I think there's lots of arguments for doing that. And so I guess what you might think of this as, there's two messages here, right? One is to really think about this fusion of and get better at fusing the old and the new, right? That's kind of the core. I think my other message was that I think many of these new applications that will be enabled by both the surplus of new capabilities at the edge and by this, embracing this, surprise notion, many of those will be low latency applications where we want lower latency. And then I was making the argument there that, well, then we could put the computation everywhere. We could have, every node in the network could be empowered to do this. And I was basically trying to say, well, why don't we focus our energy? Like if we actually got a good capability near the edge and we were able to do this 10 millisecond and we just kind of, agreed to focus our energy there, I think that would allow us to deliver a very useful, we kind of get, almost all the low latency applications we care about. So the near the edge argument is really more one of how should the community focus its effort in doing things that are, not at the core and not right at the edge. The core, there's going to be some things where the core is too far away latency wise, and some things where the edge is too expensive in terms of either power or the computational resources.
Okay, no, got it. Okay, so basically the new is the new information with the old, depending on how computation is distributed and the needs of the application, can be scattered anywhere in the network. But the key would be to identify new from old.
Yeah, I think that's the key surprise observation is this fusing the new and the old, and getting really, as I said, not so much separating, but getting really good at fusing
Combine those two.
That those are new sources of value. That's the number one thing. And then I'm kind of I guess what I'm saying is saying, yeah, look, you could do it anywhere, but if we don't focus our resources as a community, we'll probably not actually deliver anything. And that's kind of, I'm going to say, a bit of the history. The 3GPP crowd keeps talking about ultra reliable low latency, and it doesn't get delivered because it's just I think they're trying to do something that's way too hard and too expensive. And so let's back off on the requirement. And put the requirement, what I was trying to dramatize with those 1 millisecond circles, those are so big, those can be actually very big regional data centers, right? With a lot of resources that are shared, so it can be extremely cost effective. So trying to, say, okay, let's try to focus and deliver something rather than try to do it everywhere and not actually delivering.
Yeah, okay, got it. Thank you so much. Okay, I think we are almost at the end of the time, but is any last, we probably can squeeze in one more question if anyone has that. Okay, I don't see a hand rising up. So David, thank you so much for this talk. This is really interesting. And as I said, very much aligned to the overall combining information and sensors within the Enterprise New System Group. So thank you for your time. It was extremely interesting talk, and I'm sure you may get a lot more follow-up from the folks in this call.
Thank you. And I think it's a very interesting community that you formed, having gone and looked at some of the materials that you've posted. And I'm really kind of excited to see what new applications will come out of this activity.
Thank you.
Thank you.
Thank you. Bye, everyone.
Have a great week,
Thanks.
everybody.
Appreciate
Bye-bye.
it. Thank you.
Thank you.